Welcome to this presentation on one sample and paired sample t-test. This is Dr. Amanda Rockinson-Zabke, and in this tutorial we are going to discuss the three types of t-test. Then we're going to focus on the one sample t-test. We're going to talk about the definition for it, when it's used, and the formulas to calculate it, as well as how to report an APA results section. Then we're going to focus our attention on the paired sample t-test. Again, we're going to talk about the definition of it, when it's used, we're going to talk about how to calculate it, and then talk about how to report results in an APA results section, and then focus a little bit on how to set up a file in SPSS. So let's get started. There are three types of t-tests. The independent t-test, which we'll define but not really talk much about in this tutorial. The dependent t-test, also sometimes referred to as the paired sample t-test or repeated measures or within group t-test. And then finally the one sample t-test. An independent t-test is used when a researcher has one categorical independent variable with two levels and one continuous dependent variable. A researcher may use an independent t-test when they ask a question such as, is there a statistically significant difference in course points or the course score based on the type of course taken, whether residential or online? An independent t-test tells the researcher whether there's a statistically significant difference in the mean scores of two independent groups. That means they're not connected in any way. Basically, in statistical terms, when a researcher is doing an independent t-test, they're testing the probability that the two scores actually came from the same sample. This is all I'm going to say about a t-test in this tutorial. We're now going to focus our attention on paired sample and one sample t-test. The paired sample t-test, or the t-test for dependent means, or dependent t-test, is used when a researcher is interested in looking at the scores from either the same individuals who are measured two times or a pair of individuals that are matched and compared on the same characteristic. Let's talk about these two instances a little further. The researcher may use a paired sample t-test when he or she's interested in looking at the scores from the same individual measured both at before and after some type of intervention or treatment. For example, there's a pre-test and a post-test. The means of the before and after scores come from the same individual, so the means are dependent upon each other. That means they're related to one another. That's one instant in which a paired sample t-test would be used, and we're going to look at an example of this in a little bit. The other instance is the t-test. This kind of t-test can also be useful when the researcher wants to examine a pair of individuals that are matched or are compared on the same characteristics. So for example, if a researcher wanted to look at twins, or they wanted to look at a husband and wife, the means are dependent here because they're from individuals who have been matched on the same variable, and the paired sample t-test uses differences between each pair scores to construct the comparison distribution that is used with hypothesis testing. But we'll talk a little bit more about this in a moment. So we've determined that an independent t-test is used when a researcher wants to look at the difference between two groups on one score and has one independent variable and one dependent variable. We've determined that a paired sample t-test is used when a researcher wants to look at either matched pairs and compare two individuals that are matched, or wants to look at a set of scores from one individual in which there's one categorical independent variable, usually time 1 and time 2, and one dependent variable. Now let's talk a little bit about the one sample t-test. The one sample t-test is the t-test that's probably most similar to the z-test, which is usually learned by most individuals when they first start studying statistics. A researcher uses the t-test, just like oftentimes the z-test, when he or she has one sample and wants to compare that sample to the general population, and the general population mean is known. Now, I said the one sample t-test is like the z-score, but it's also different in several ways. Oftentimes, a one sample t-test is chosen over a z-test because the sample size that's being looked at is less than 30. So the sample size isn't large enough to run a z-test. So it's important to remember that. Also, because of the small sample size, when you're working with a one sample t-test, the small sample size doesn't give enough information to compute an unbiased estimate of the population standard deviation, or what often people term sigma. Therefore, the population standard deviation needs to be estimated using degrees of freedom. And so that makes it different than the z-test. Also, the comparison distribution used to determine whether or not there's a significant difference is called a t-distribution rather than a z-distribution. But we won't get into all of that now. We're going to talk about formulas and calculations in a moment. Here it's important for you to understand that a one sample t-test is used when you have a smaller population, or a small sample size, not population, sample size. And the researcher wants to compare a sample to the general population. Now, before we start discussing the one sample t-test as well as the paired sample t-test more in depth, let's take a moment and talk about assumption testing. Remember, with the parametric analyses, you need to meet certain assumptions for the test to be robust. For both the one sample t-test as well as the paired sample t-test, the primary assumption that you need to test for is normality. And remember, normality assumes that the population distributions are normal. The t-test is often robust, both t-tests are robust in the face of moderate violations of this assumption. For example, if you have a sample over 30 with a paired sample t-test, or a sample over 50 with a one sample t-test, it's still fairly robust even if it's not exactly normal. Remember for a moment, when you're looking at normality, there's two primary ways that you can test for normality within the distributions. For the paired sample t-test, you're specifically looking at the distribution of the pre-test and the distribution of the post-test, or the distribution between the matched individuals on each score. For the one sample, you're looking at your sample that you're looking at that you're going to compare to the mean. You can check normality in these distributions in two ways. You could use a histogram as pictured here. We can see that this histogram demonstrates that this distribution is normal. The other normality test you could use is something such as Shapiro-Wilks if you have under 50 individuals, or the Kolmogorov-Smirnov test if you have over 50 individuals. Again, just as a reminder, for the histogram, if normality is assumed, what you're going to see is more that symmetrical bell curve like you see here in this picture. On the normality test, non-significant results, that's results that have an alpha over 0.05, indicate tenability of the assumption. That is, normality can be assumed. Now, there are a few more assumptions that need to be met, so let's take a quick look at those. For the paired sample t-test, there are three additional conditions or assumptions that need to be met or should be met. One is that the sample is randomly selected from the population. Next, the dependent variable is continuous. It's measured on an interval or ratio level. And also that the two levels are independent variables or observations, not necessarily independent groups, but independent observations. So, for example, the pre-test and post-test, or the husband and the wife. Then for the one sample, the additional assumptions include the samples randomly selected from the population, and also, again, the dependent variable is a continuous variable. It's measured on an interval or ratio level, not a ordinal or nominal level. So now that we've covered assumptions, let's take a look at the one sample t-test. Remember that a one sample t-test compares the mean scores of a sample to a known value, usually the population mean. Really, a one sample t-test compares the observed average, what's seen in the sample, to the population average, the expected average. Let's take a look at an example now. Let's say that a researcher wants to know if students in rural Appalachian perform as well on their SATs, specifically their writing SATs, as the general population. So specifically, the researcher wants to compare the mean SAT writing scores of high school students from a small rural Appalachian school to the mean writing SAT scores, or the mean SAT writing scores of the general population. So after doing some research, the researcher quickly finds the mean SAT writing score for the general population. However, the population standard deviation, or sigma, is not so readily accessible. So he has that standard. He doesn't have the standard deviation. He's going to need to calculate it. He has the general population mean, and then he takes a random sample of, let's say, 10 high school students from the rural Appalachian local high school, and he calculates the mean and the standard deviation. Since he has a small single sample, he knows the population mean, or the population mean is known, but the population standard deviation is not known. The one sample t-test is the perfect analysis for him to determine whether or not there's a statistically significant difference in writing SAT writing scores of students in rural Appalachian compared to the general population. So, after determining that the one sample t-test is the appropriate analysis for this researcher, the researcher's going to write the null hypotheses, or test the null hypothesis. And the null hypothesis in this scenario is that there is no statistically significant difference in the mean SAT writing scores of Appalachian students as compared to the general population. Again, the null hypothesis states that the mean of the sample population is not different from the mean of the general population. That's what the researcher's testing. Then he proposes the alternative hypothesis, that there will be a statistically significant difference. And remember, the alternative hypothesis states, or the research hypothesis states, that the means are different. They're not equal to zero, that there'll be a large difference, or there'll be a difference between the general population and the sample population. Now that we understand that a one sample t-test can be used to compare the mean scores of a sample to a known value, usually the population mean, let's take a look at how to actually calculate the t-value. Now we're going to look at how to perform a one sample t-test in a very step-by-step manner. The first step being estimating the population mean. So once the researcher has stated the null hypothesis that's going to be tested, gathered the data, the information from the sample needs to be used to estimate the population variance. Because the sample is small and the population variance is unknown, here you can see that the sum of squares is divided by the degrees of freedom of the sample, or n minus 1. This number is one less than the total number of participants in the sample. So, for example, let's say that the sample consisted of 10 participants. Then the degrees of freedom here would be n minus 1, 10 minus 1, or 9. The population standard deviation then is equal to the square root of this estimated variance, because remember, the standard deviation is always the square root of the variance. Now let me take a moment here and stop and talk a little bit about why we use n minus 1. Remember, here it's important to note that a smaller sample size is used, usually a sample size of less than 30. And it turns out, for reasons I'm not going to go into depth here, that the sample standard deviation is really a biased estimate of the population standard deviation. The sample value is consistently smaller, actually, than the population value, and this has to be corrected in order to provide a more unbiased estimate of the population standard deviation. So for this reason, the formula here for standard deviation is altered for the t-test in order to provide a larger number. And this is really accomplished by dividing n minus 1 instead of n. So as you can see here, dividing by n minus 1 results in a slightly larger value. So for example, instead of dividing it by 10, we're dividing it by 9. Thus, providing an unbiased estimate of sigma. So this n minus 1 here is called the degrees of freedom. So n minus 1 is used because it helps provide an unbiased estimate of sigma. Now, because the researcher has estimated the population variance and the standard deviation using the degrees of freedom, the shape of the comparison distribution of the means will be actually a t-distribution. Remember I said that a t-distribution is used instead of a z-distribution, for example, in a z-score. And the t-distribution is basically a distribution of the sample means, and it's constructed using the estimate of the population standard deviation instead of the true population standard deviation, sigma, as is often done with a z-distribution. Now, on to our second step here. Here in the second step, as you can see, we have the formula for calculating the standard deviation of the distribution of sample means. This value is often called the standard error of the mean. Most statistics texts that you use use the notation S sub m to represent this value. The formula uses the estimated population variance that was computed or calculated in step 1, and this is divided by the sample size, or n. Then you take, or the researcher would take, the square root of this value, and the result here is then the standard deviation of the distribution of means. The value sub m is important because it is used to calculate the sample's t-score that we're going to talk about later. So before calculating the t-value for the sample's results, first a researcher must determine the critical or cutoff value that will mark the rejection region. That is, whether or not the researcher will reject or fail to reject the null hypothesis. This is determined by looking at a t-table found in most statistical texts. The cutoff or t-value from the table will depend on a few things. So whenever you or the researcher goes to the t-table, they need to keep in mind whether or not they're doing a one-tailed or two-tailed t-test, the degrees of freedom of the sample, as well as the chosen alpha level. For educational and social science research, this is usually a 0.05. So in the table, when looking at the table, the researcher will find the degrees of freedom in the table and then move across the column to find the t-value. Any t-score more extreme than this value can be considered statistically significant. If the researcher is conducting a one-tailed test, he or she needs to make sure whether the t-score is negative or positive depending on the direction or the tail of the distribution that he or she is looking for. And then remember, for a two-tailed test, the researcher will be looking for both the negative and positive values of the cutoff t-score, because the researcher is looking for a difference in either direction, not just one direction. So once the t-value or critical cutoff t value is determined, it's time to actually start calculating the t-value for the sample. So the sample's t-score is calculated by simply subtracting the known population mean, or mu, from the sample's mean and then dividing it by the standard deviation of the distribution of means that, remember, was calculated in step 2. This t-score is then compared to the critical or cutoff t-value that was previously determined in step 3. And remember, based on our discussion when we talked about step 3, that if the sample's t-score that was calculated in the previous step is more extreme than the cutoff t-score, then the sample score lies within the rejection region and is considered statistically significant. Therefore, the null hypothesis can be rejected, the alternative hypothesis is supported, and there's a difference between the sample means and the population means. However, if the sample's t-score is not more extreme than the cutoff, it lies outside of the rejection region, the null hypothesis is failed to be rejected, or you fail to reject the null hypothesis, and there is no difference between the sample and the population. After it's determined whether or not the t-value is statistically significant, the next step is really to calculate the effect size, that is, determine the practical significance of the results. The formula for computing effect size for the one sample t-test you can see here. It's actually very similar to the effect size formula for the z-test. So if you're familiar with that, this should look familiar. However, instead of using sigma in the denominator, here you can see we use the estimated value of the population standard deviation, or S, that we actually figured out in step 1 when we were talking about calculating the t-test. Note that we're not using S sub m here, the standard deviation of the distribution of means, but we're using S. And the reason we do that is because it's the best estimate we have of the standard deviation of the general population. So once this formula is used to calculate the effect size, then as the researcher you need to use Cohen's conventions to decide whether or not the effect size is small, medium, or large. If it's a 0.5, then we can say it's a medium effect size. 0.2 small, 0.8 or above is a large effect size. So now we've looked at how to calculate a one-sample t-test. To better understand the logic behind it so we can better interpret it, let's take a look at how we would actually set up the data set in an SPSS file. The reality is that it's important for us to understand how the one-sample t-test is calculated so that we can better explain it and interpret the results that we get. However, for the most part, as a researcher, what you're going to be doing is actually doing the calculations in a statistical software such as SPSS. Here you can see that the data set corresponds with the one sample t-test example that we've been looking at. Here we have a hypothetical list of the number of SAT writing scores for our sample of 10 participants from the high school in Appalachia. The only scores involved in this study are those scores of those 10 participants. So this is what a data set for SPSS would look like. Now let's talk a little bit about taking the results from SPSS. We're not going to go over SPSS now, but we're going to talk about taking the results from SPSS and putting them into an APA results section. So what needs to be reported for a one samples t-test? Well, the results of your assumption testing, the descriptive statistics for the sample, both the mean and the standard deviation, and then the known mean for the population, the number of participants, the degrees of freedom, the t-value, the significance level, and the effect size. Let's take a look at some of these items a little bit further. In stating the statistical results, here you can see you're going to report the t-value, the degrees of freedom, the alpha level, as well as the effect size. Then once it's stated in statistical terms, it's important that the researchers state the results in a full sentence. So for example, looking at this information here, what we can see is that the t-value is 2.37, and since the alpha level is 0.02, it's less than 0.05, we can say that the results are statistically significant. And in Cohen's d, the effect size is 0.10, so it's small. So in written sentence, we may say something like the following. The students who lived in the Appalachian area had a statistically significant lower SAT writing scores than those in the general population. And the reason we say it's statistically significant is because the alpha is less than 0.05. By looking at the means, we can tell which group actually scored higher. Our sample scored lower than our general population, or our general population scored higher than our sample, and we can say that the effect size is small. Finally, when writing an APA results section, it's also important to state a decision about the null hypothesis. And here we can say that the t-test provided evidence or provided support to reject the null hypothesis and state that there was a statistically significant difference. So now that we've discussed a one samples t-test, we talked about the definition, when it's used, looked at the formula, and talked about how to set up an SPSS data set as well as the results section, let's turn our attention to the paired samples t-test. Remember, also often called the dependent t-test and sometimes referred to as the within or repeated measures t-test. Remember, this t-test is used when a researcher is interested in looking at or comparing scores from the same individual who's measured 2 times, or a pair of individuals that are matched or compared on this similar characteristic. Let's take a look at an example of when a dependent t-test may be used in research. Let's say that an educational researcher notes in the literature that graduate students struggle in advanced statistics courses, and it's well documented that this struggle is related to a lack of understanding of basic concepts. So an educational researcher develops an online workshop to help individuals improve their statistical knowledge of basic concepts. This workshop also teaches students skills and techniques for successfully completing statistics courses. So the researcher wants to know whether or not this workshop that he developed will improve individual graduate students' statistical knowledge. So there are different ways he could set up this experiment, but let's say that he decides to have 10 students participate in the workshop. Prior to participation in the workshop, he assesses their statistical knowledge using a statistical assessment. He gives them the workshop, he has them practice the skills and the techniques, watch tutorials to develop knowledge, and then gives them a post-assessment a week later. Now, in this experiment set up like this, the two samples of interest in this scenario are the two sets of scores. The score or the assessment, the scores to the assessment that was given before the workshop, and then those given after. And because these scores are from the same sample, the pretest and posttest, they're from the same sample, the samples are considered dependent. So we can look then at the amount of change between the scores and use them to determine whether or not the actual workshop was helpful. So this is basically what a dependent t-test does for us in a very, very simplified manner. What it does is it helps us understand the difference in scores on a pretest and a post-test. So, as illustrated in this example, a paired sample t-test is aimed at finding the differences in scores. In this scenario, it was whether or not there's a difference in scores before and after treatments. Remember, we also talked about a paired sample t-test can be applied to matched pairs, such as looking at the difference on a score between a husband and wife or twins. However, in this scenario, what we see is that the null hypothesis is going to be stated in words such as this. There's no statistically significant difference in graduate students' scores on a statistics assessment before and after participating in a one-week online statistics workshop. A difference score of 0 here represents no change between time 1 and time 2, or the pre-test and the post-test. So really the null hypothesis is saying that the difference score is hypothesized to be 0. There's no difference. The alternative hypothesis then is that there's a statistically significant difference in graduate students' scores on a statistics assessment before and after participating in a one-week workshop. Here we see our research hypothesis. We're saying that the type of difference is not going to be equal to 0. For the paired sample t-test, it is that column of different scores that we're really, really interested in, and we're going to go over that in a few moments. But it's important to understand that the paired sample t-test can be used whenever you're looking at the difference between pre-test and post-test, or the difference between a matched pair. So in order to look at this change or this difference, the researcher, or we must compute what is called the difference score. And this concept, or this idea of difference score, is actually fairly easy to grasp, as you can see here. It's simply one score minus another score, or the difference between two scores. In the example we just looked at, in a before and after type study, the difference score equals the difference between the after score and the before score. For a paired participant study, or a matched participant study, the difference score equals the score of one subject minus the score of another subject. So if we were looking at twins, it would be twin 1 minus twin 2 on a specific measure. Let's take a closer look at this as we talk about setting up a data set for a paired sample t-test in SPSS. Here you see an example data set using our online statistics workshop example. This is what your statistics data set would actually look like in SPSS. Here we have two sets of scores for the same 10 students. The first column shows us the statistics assessment scores before the students took the workshop and learned their special skills and technique and knowledge. And the second column shows us the student scores on the statistics assessment after they learned the skills and techniques, after they took the workshop. So remember, our main question is this, whether or not there's a difference between their statistics knowledge scores or statistics assessment scores before and after treatment. So in order to find this out, remember I just said we need to compute the difference scores for students by subtracting the after treatment minus the before treatment scores. And this is what we see in the third column here, those difference scores. So 5 minus 4 in the first row equals 1. In the second row, 3 minus 1 equals 2, and so on. So from this point on, it's the difference scores that we're really going to use to conduct the paired sample t-test. So it's important to keep this in mind as we walk through the steps of conducting a paired sample t-test. As we walk through computing a paired samples t-test, what you'll notice is that it's very similar to computing the one sample t-test. Let's look at this first step. The main difference here is that you will use the difference scores from the sample, the mean of these different scores, as the sample's mean for your calculation. This is different than what we did in the one sample t-test, where we just use the mean of one test score. So you calculate the mean difference. Then to compute the mean difference of the scores, find the difference for each subject or each pair of subjects, and then you compute the mean of these differences using the formula shown here. So the sum of the difference divided by n. Now step 2 should look very familiar. As with the single samples t-test or the one sample t-test, we estimate the population variance using the formula that includes the degrees of freedom of the samples in the denominator. In the case, however, of the paired sample t-test, the mean we use here is the mean of the difference scores. Everything else basically works the same as it did for the one sample t-test. We plug in the values to find the variance. Then, once we find the variance, we take the square root of that value to estimate the population standard deviation. Next, we find the variance and standard deviation of the distribution of the means by dividing the estimated variance from the step 2, what we just completed, by the sample size n, and then taking the square root. Now, before calculating the t-value, we need to use the t-table found in the statistical textbook to find the critical cutoff t-value, just like we did in the one sample t-test. Now it's time to calculate the t-value for the sample. Remember here that the population mean in this formula, mu, is going to be 0 because it represents the comparison population that has no difference between scores. This is divided by the standard deviation of the distribution of means. And this will give you your t-score, which you will compare to your cutoff or critical t-value to determine whether or not your results are statistically significant, to determine what conclusion you can make. Based on the t-value in comparison with the critical t-value, the researcher, or you as the researcher, either reject or fail to reject the null hypothesis. Remember, the sample's t-score that's more extreme than the cutoff t-score lies within the rejection region, and therefore the results are considered statistically significant, and the null hypothesis can be rejected. However, if the sample's t-score is not more extreme than the cutoff, it lies outside of the rejection region. So you fail to reject the null hypothesis and say that the results are not statistically significant. So deciding whether or not to reject or fail to reject the null hypothesis is determined by calculating the test statistic. We just looked at how to do this. We calculate the t-value, we compare it then to the critical t-value. However, when you calculate a paired samples t-test in SPSS, SPSS will give you in the output the t-statistic as well as the p-value associated with that statistic, or the alpha level associated with that statistic. And you're going to use that alpha level to determine whether or not to reject or fail to reject the null hypothesis. If the alpha level is equal to or less than the a prior significance level set, then you have evidence to reject the null hypothesis. In other words, usually since we use a a 0.05 significance level, if this p-value or the alpha level is below a 0.05, then you reject the null hypothesis. If it's above a 0.05, if the alpha level associated with the t-statistic is above a 0.05, you fail to reject the null hypothesis and say that you have no statistically significant difference. So now we've talked about statistically significant difference. Let's focus on practical significance and the effect size. Actually, before I discuss the effect size, let me make one more note about the previous slide, and it's this. Remember that SPSS does all the calculations for you. So what we just talked about in terms of calculations, SPSS is doing that for you, and then basically doing the comparison between the sample's t-value and the critical t-value, and determining whether or not the t-value is significant. So SPSS is simply just doing all the calculations for you and then giving you that significance level. So I just wanted to bring that to your attention. So let's talk now about what we see on this slide, and that's the effect size. After determining if a t-value is statistically significant or a statistically significant difference exists, you'll want to compute an effect size to determine the practical significance of your results. And the effect size is determined in the same way that we figured out the effect size for the one sample t-test. You can see the same exact formula there. The sample's mean will be the mean of the different scores. The known population mean is 0, and S is the estimated standard deviation that was determined or calculated in step 2 that we talked about prior to this. So once you take that formula and you calculate the effect size, you then use Cohen's 1988 conventions to interpret that effect size. So now we've talked about calculating the t-value and statistical significance, the effect size. Let's talk about how to report all of this in an APA results section. Here you see a list of all the items that need to be reported for a paired samples t-test, and as you'll note, it's the same list as we looked at as the one sample t-test. So the assumption testing needs to be reported. Remember, normality needs to be reported, and you can do that using the histogram or Shapiro-Wilks or the Smirnoff test. Descriptive statistics, the mean and standard deviation for both the pre-test and the post-test, or the matched pairs. The number in the sample, the degrees of freedom, the t-value, the significance level, as well as the effect size. And just as we discussed with the one sample t-test, here are some basic guidelines to use when you're writing up information or writing up an APA results section for a paired samples t-test. Don't forget to state your statistical results, the t-value, the alpha level, the effect size. Remember to state the results in a sentence form. So, for example, students scored statistically significantly higher, let's say on the statistics post-test as compared to the pre-test. And if we look at Cohen's D here, if a 0.6, we can say that it's moderate or moderately large. Also, don't forget to look at the alpha level and make a decision about the null hypothesis. The t-test here provides evidence that we can reject the null hypothesis because the alpha level is less than 0.05. So when you're writing up the results for an APA results section for a paired sample t-test, don't forget to state the statistical results. Tell what those results mean in sentence form. You know, was there a statistically significant difference? Was there not? And talk about, was the pre-test higher than the post-test? Was the post-test higher than the pre-test? And this can be determined by looking at the mean scores, or in the matched pair, did one individual score higher than another individual? And then don't forget to state the decision about the null hypothesis. This now concludes our tutorial and discussion about the one samples t-test and the paired samples t-test. So in summary, let me remind you what each of these analyses are used for. Remember that a one sample t-test compares the mean scores from a sample to a known population. So as a researcher, if you want to know how a specific population compares to the general population, you would use a one sample t-test. A paired sample t-test compares the mean differences between two scores from different times or from different subjects or different participants who are matched. And so, for example, as a researcher, if you want to know how individuals score on a pretest as compared to a post-test after an intervention, a paired sample t-test would be used. Or if you want to know how a husband and wife differ, let's say in terms of marital satisfaction, a paired sample t-test would be used.